The emission of alpha, beta and gamma radiation has already been covered in IGCSE, but there's a number of small but very important additions that we need to cover at A level. And we're going to start off by thinking about alpha, beta and gamma and considering energy conservation and some of the other laws of conservation that you don't yet know about. During alpha decay, the nucleus emits a helium nucleus, 2 protons, 2 neutrons. In this equation, americium-241 decays to helium-4 and what? Well, what do we know? Its proton number must be 95 minus 2 is 93. So using a periodic table, that makes it neptunium. We're going to need to balance a few things in this reaction as things are conserved. The nucleon number. This is conserved. So 241 becomes 237. Oh, and remember that 237 is also called the mass number. And that's because it's the total number of nucleons in the atom. It's not the mass though. It is just a count of the particles. So what is a mass? Well, if protons and neutrons had the same mass, life would be far too easy. They're actually slightly different, with protons being a little more stable and hence having slightly smaller masses. They are pretty close though, so to make life simple, we have a quantity called the unified mass constant, which is about the mass of a proton and neutron. Okay, unified atomic mass constant. So in summary, neptunium has 237 nucleons, and we can say it has a mass of 237 U. That's 237 unified atomic mass constants. As we're balancing things off, so the helium is going to have 4, isn't it? That's why we got down to 237 here. Conserved. Charge is also conserved, which is why the proton number needs to be conserved here, as we are dealing with nuclear reactions. Remember, there's no orbital electrons because it's the nucleus. Mass energy is also conserved, and momentum, and a thing called the lepton number, but more on that later. Conservation of momentum means that assuming that americium was stationary at the start, if the helium nucleus was ejected to the left, the neptunium would have to move to the right. This can provide us information about the relative masses of the two child particles, giving us crucial information about decay particles that we cannot actually see. Since mass energy is conserved and there are no other emissions, the alpha particles produced all have exactly the same discrete kinetic energy. So, like I drew before, we can imagine a parent nucleus splitting to form 2 child nuclei. It's quite a violent rupture and leaves the neptunium nucleus in an excited state. That's proper terminology, by the way, that you should learn to use. An excited state means that the nucleus is not in its lowest energy state. So, it might decay again, this time releasing energy as a photon of electromagnetic radiation, which is gamma radiation. Like all radioactive nuclear decay, this process is random and spontaneous. Note how the equation is properly balanced, with a small asterisk used to denote the excited state. Lastly, but certainly not least at A level, is beta. We're going to be digging into this quite a lot later on, but the basics are to again consider conserving those quantities. An electron is emitted in beta minus decay, which is not a nucleon. That beta particle is not from the nucleus. So the product from strontium-90 is still going to have 90 nucleons. In nuclear equations, we're kind of using the proton number to indicate charge. So the electron is written with -1, giving us 39 for the product. So that means a neutron changed into a proton, which is weird. A neutron changed into a proton. Now I'm going to do a whole other video looking into that, so let's just go along with it for now. A neutron changed into a proton and created a brand new, never before seen electron. Now remember, this is nuclear physics. There are no orbital electrons. This beta particle, an electron, did not exist a moment ago. It was created. Now, do you remember earlier I mentioned something called the lepton number? And that lepton number is also conserved. Now, lepton is the name for a group of particles, and electrons are in that group. Electrons are a kind of lepton. In this beta minus decay, we just created a new lepton. So we need to balance the equation somehow. And we're going to do that by introducing antiparticles, specifically an antineutrino. Neutrinos and antineutrinos are leptons as well, and you can think of them as basically being like an electron with zero charge. So if we have an electron and a neutrino, we have two leptons. So that means we've got a lepton number of 2. 3 electrons and 2 neutrinos, that's a lepton number of 5. But 1 electron and 1 anti-electron, that's a total lepton number of 0. The electron and its antiparticle have the same mass, but opposite charge, by the way. Okay, and the electron has a lepton number of 1, the anti-electron has a lepton number of -1. For the reaction we've been looking at here, the important bit for now is that 1 electron and 1 antineutrino gives a lepton number of 0. So the beta minus decay equation is actually going to be strontium 90 decaying to yttrium 90 plus an electron plus an antineutrino. Now, if we try to balance its momentum, it's all getting quite more complicated than before. With 3 child products, we cannot be certain how the momentum will be divided amongst them. And this also means, importantly, that the beta particles will have a continuous range of kinetic energies. This contrasts with the alpha particles, which had discrete values. That's a lot to take in, on top of everything that we've been covering in GCSE. But take your time, review the material and try to get a head around it, because in the next few lesson videos, we're going to start getting into the weird and wonderful world of quarks and how the family of subatomic particles fits together.